In this video we discover point AABB collision detection. Although testing only a point in space is very inaccurate and could cause strange glitches, but is also very efficient and fast to compute and lays out the foundation for other collision testing methods. Hi, my name is Alex and this is another video in the series about collision detection for 2D games, so let's get started. We begin with a point W in space that need to be tested against the box. The AABB is represented by two vectors, a vector that references the maximum extent of the box and a vector that represents the minimum corner of the box. The AABB will never rotate. Let us compute the two other vectors from the min and max vectors. The first is the center vector C, which represents the center point of the box. The resulting vector is just at the halfway of the added min-max vectors. The second is the extent vector E, which is the half vector of the vector between the min and the max vectors. Together those two vectors could be used as the AABB representation in the first place. The transformation matrix M of the AABB would look like this. It is only a translation matrix carrying the translation vector C in its augmented column. The inverse is also very simple. It is just a backwards translation which led to the point C. Because the AABB is not rotated, we can simply transform any vector into AABB space by just subtracting the just computed center vector C from the point W, resulting in the local point V. Having transformed into local point V in AABB space, we can draw from the perspective of the AABB now. The next step would be to test if the relative point V is inside the box. At this point, we could just test with if statements if the point could be inside, but we can go a step further mathematically. Since the corners are involved, to test if the point V is inside, we can further transform into AABB corner space. Because the corner is not rotated, the forward transformation could be an identity matrix combined with the extent vector E, which translates the corner point. Now we have the forward transformation. We can invert the transformation matrix M, which allows us to transform into corner space. The inverse transformation is simply the backwards translation of the extent vector E. A local AABB point V would transform into a corner distance vector D. Looking closely at the inverse row vectors, we can see the line equations that make up the corners. So let's extract those line normals, which are an x in x direction and y in y direction. Knowing there has a line normal form, we could have constructed those vectors in the first place without constructing the transformation matrix. But you may find it interesting how those line normals emerged from the inverse transformation matrix. The next step would be to check the opposite lines of the box. Let's first acknowledge that the distance to the line in negative x direction is the same as the distance in positive x direction. So the Hesse normal form of the negative line equation has just the direction vector flipped. Technically, we are required to test against every normal of the box's bounds. That is, test the point for every normal. But looking at the picture more closely, we could optimize by just considering the normals pointing in the direction of the point to be tested, because the other two lines are facing away from the point, no matter if the point is inside or outside the box. So what we really need is to test only two normals that can differentiate if the point is inside or outside. Those normals are the one facing the point. Now let us point out the fact that every normal has the distance to its box bound stored negatively. That is minus EX and minus EY. We know from the normal equation that we need to subtract the orthogonal distance from the projected point in order to make up the distance to the offset line. Another point to make is due to the fact that an AABB is not rotated and that its normal only contains positive and negative ones. We can take this fact to our advantage and construct the normals we need to test against. Because the normal vector V is already in the AABB space, we could simply take the sign of the components of the vector and use those for the normals. This way we always end up with normals facing the point we need to test. The distance in the augmented component of the normal can simply stay the same. Computing the scalar product in order to gain the distance to the line for the intersection testing, we simply write out the equation and see yet another nice property. The fact that the sign component is always multiplied with the component the sign comes from leads to the fact that this part of the equation is never negative. In other words, the local vector v will always stay positive no matter which normal is chosen. We can express this by using the absolute operation on the local vector v when computing the distance vector d. So computing the distance to one of the bounding box's lines, we can always use abs v minus e. Having the distance vector, we now can determine if the point is inside the box or not. That is, if any of the components of D are greater than 0, the point is outside, otherwise the point is inside. Or if all components of D are less than 0. Because we produced the normals already in our computation, we can simply choose which normals we will take for a collision response. That is the normal that has the greatest distance to its normal. If the component dx of the distance vector D is greater than the distance dy, we can take the normal in x direction. Otherwise, we take the normal in y direction. Note that computing the normals is only required if the point and the box happen to intersect. Otherwise, we can eliminate that unnecessary normal construction. As you just saw, computing the point AABB intersection is just that simple. A single simple equation allows us to do the test. I hope you liked the video and you tune in next time. Stay safe and bye now.